Okay, my friends, let's actually go back to IQ scales for a moment. You might be a little bit sick of them after yesterday, but they give us a great data set with relatively nice numbers to explore these regions in between those whole numbers of standard deviations we've been talking about for so long. So let's use this data set and dive in.
Okay, I've taken the liberty of adding our bell curve back on the board with our the IQ test score average of 100 and then plus or minus the 15 going up or down depending on how far you want to go. Now using this scale that I'm looking at here, there's a couple probabilities we can get just from looking at this chart. For example, the range that is significantly above average, you have to have a score that's more than 130. Okay, so 130 is right here. In order to be significantly above average, you have to have a score that's more than that. Now, whether or not equal to 130 and more than 130, whether or not you should include 130 is irrelevant because this is continuous data. We had this discussion yesterday. There's no number right next to 130. So what the normal distribution does is it just says, to hell with it, I'm going to shade starting at 130 everything to the right. All the way out into the tail. All the way out into the tail. Now, how much of the curve did I just shade? Well, we can figure this out based on stuff we already know, right? We can figure out what that is because of some old information. We know that since this is average, I'm going to put the z-scores, or those numbers of standard deviations, under this. We know that 100 is 0 standard deviations. So the raw score of 100 has a z-score of 0. 115 is 1 standard deviation up. 85, is 1 standard deviation down. 130 is 2 standard deviations up. 70 is 2 standard deviations down. We know that. We know that from before. We also know something else. This area right here represents 95% of the curve within 2 standard deviations. That means these two areas here are the other 5%. Which means this area right here has to be 2.5%. Which tells us that 2.5% of the population by this IQ measure, which is the most recent one I could find, by the way, 2.5% of the population are considered significantly above average. Boom. Now, how about those that are significantly below average? I'm going to leave this one up here just for reference. Well, those are the ones that are less than 70. So, that's these folks. Well, remember, this curve is symmetric, even though it doesn't look like I drew it that way, and I apologize. I apologize. We're going to use computer technology here to draw us a perfect graph in a minute. So, yeah, that area has to be the same as this area. So that means there are 2.5% of people that are also considered significantly below average. One quick aside, the very nature of the symmetry of this curve is why no one that teaches should ever grade on a curve. If you've ever taken an exam and somebody's added points to you, to your exam score and said, we're curving the exam, that's actually not curving the exam, that's just adding points to your exam. Curving an exam means you grade it like this. It means the majority of the students will get a middle grade, which is a C. And the same number that get A's will get F's. It's a horrible, horrible, horrible way of approaching grading. Anyway, now let's clear the board and then come back and look at some of these other ranges. Okay, so if you look at the chart, to fall in the range of average, you have to be between 90 and 110. Now, don't confuse that word average, which is this IQ scales calling someone average, with the actual average of all IQ test results. That's the truth. The truth of these test results is the average will be 100. But to be called average on an IQ scale, that means you have to fall between 90 and 110. Now, where are they? Let's get some color in here. Where are they? Well, 90 is about here. And 110 is about here. The first thing I hope you notice is that 90, I'm going to move these over, 90 and 110 are the same distance from 100, even though I didn't didn't draw it that way. Mathematically, they are. They're both, well, this one's 10 down and that one's 10 up.
So to be considered average,
we've got to figure out what percentage of the population, which is that green area right there, what percentage of the population is between 90 and 110? Well, that's a fantastic question now, isn't it?
well, heck yeah, it's a great question. As a matter of fact, I think we need a better picture. So here's actually a computer-generated image of that range, 90 to 110. Let's deal with this by zooming in on that axis for start. That's a little bit easier to see. Okay, now, what makes this challenging is that 90 to 110 is not a whole number of standard deviations, but we can still figure out how many standard deviations it is. So we know that the distance between 85 and 100 is 15. That's because the standard deviation of the entire distribution is 15. The distance from 90 to 100 is only 10. That means that 90 is 2/3 of a standard deviation down from 100. Similarly and symmetrically, the distance from 100 to 115 matches the distance from 85 to 100. That's because that's the one standard deviation range. Well, the 100 to 110 is also 2/3 of the way. So 2/3 of a standard deviation from average. So in a similar way that we said 85 to 115 is one standard deviation from mean, 90 to 110 is 2/3 of a standard deviation from mean. I don't know about you, but this is getting a little bit hard to look at. There's a lot of markups. There's this caret. Let's switch over to the standard normal distribution and see how much cleaner this actually looks. Okay, that's better. Oh, we are missing something though. Better add them in. Oh, good. Okay, so now it's the same thing as before, except it's much cleaner, which means we have a much easier way of seeing what 2/3 of a standard deviation is. Now the question remains, how much area did we just shade?
And that is the challenge. How do you figure out 2/3 of a standard deviation's areas? We only know one standard deviation is 68%, and two standard deviations is 95, and three standard deviations is 99.7. We don't know all the other standard deviation measures, which is fine. We don't need to. We're going to have a tool for that in a second. Reasoning through it, some students tell me, well, if it's 2/3 of a standard deviation, then just take 2/3 of one standard deviation. Mathematically, that can't work. It's a great idea. Just first of all, it's a great idea. But it can't work mathematically because this curve is exponential in nature. As you'll see if you watch the end videos, it's got an exponential feature in it, which means it's not linear. If it were linear, we could totally do that, but it's definitely not. It's got these, it curves. It doesn't go in a straight line. Now, due to its nature, and due to the fact that if you think back to how we got the 68% and the 95% from before, we were actually counting up data points. We weren't doing anything exact. We were actually approximating to get those ranges, and then you had to Google what the empirical rule was. The reason these are hard to get is because the way to get them, and you'll see this if you watch those last videos, is through a series of effectively infinite additions, where you have to, instead of just shading like this, you have to shade one line at a time. Now, I know what some of you are thinking. You're going, wait a minute, you just said there's infinitely many points between here. How do you draw infinitely many lines? One word, calculus. But there's no calculus in this class, so don't worry. In the past, the way we've done this is by using tables in the back of textbooks. Since it's not 1986 anymore, we're not going to do that in here. And I've actually built you a tool to figure these areas out. Let's go take a look at how to use that tool right now.